Hi everyone, today we're going to be looking at what we call a quadratic graph. Now a quadratic is a graph that has the highest power being a power of 2, okay? And what that does to our graph is it actually makes it a non-linear graph, and that just means that it's not a straight line, okay? This means graphing them can be a little bit trickier and they do look a bit strange compared to our usual linear graphs. Now, some really important things to note in this formula here is that we have three things that affect the graph, how it looks, how it moves. Okay, this is the typical form for a quadratic, and luckily enough, this c value at the end is still our y-intercept. So that still matches up to our y equals mx plus c, with that still being our y-intercept at 0, c. And that's because if I now sub in x equals 0, ax squared and bx squared both become 0. So we're left with c. The other one, which is what we're going to focus on for today, is this a out the front. Okay, now this is called a dilation factor. And you don't have to worry too much about why it's called a dilation factor or how we find it. You just need to know how to use it. And dilation just talks about how much it stretches or narrows, depending on what that A is. Now, we'll have a look at some examples of just ax squared, so without the bx and without the c. These ones here are all in the form y equals ax squared, and that orange graph right here is the kind of standard quadratic, or standard parabola is another word for it. So this is one where we haven't dilated it and we haven't moved it left, right, up, down. Okay. This blue graph here has been dilated by a half, so it has been dilated. And what you'll notice is even though it's a half, it makes it stretch outwards. And that's because if I'm halving every value, it's going to climb a little bit slower, so it becomes wider. Now, these two at the bottom, I've got negative a quarter x squared, has once again been dilated. It's been stretched out and made wider. But this negative out the front has also done something quite interesting. And what it's done is it's reflected that standard parabola we've got, and it's reflected it in the x-axis. So it's just flipped it like the x-axis is a mirror, okay? And this purple one down the bottom is the standard reflected parabola, okay? So all your y values are now negatives instead of positives, okay? So this is just your standard y equals ax squared form. Now, if we move on, we now have our y equals ax squared plus b form. So these ones are when we've taken this b, which is the c from before. So you might want to write this as ax squared plus c instead, okay, if you don't want to get those confused. Now, what's happened here is this is called a translation. And you don't have to worry too much about the key terminology at the moment, but a translation just means that it's been moved. It's been moved left, right, up or down. And what the B does in this situation is it moves it up or down. And what that does is that affects the number of x-intercepts. Okay, so if you think back to the graphs that we had before, that y equals ax squared, they all had the one x and y intercept that was shared at 0, 0. But parabolas don't always have one intercept like linear graphs do. Let's have a look at this orange graph here, that x squared plus 3. That one has one y-intercept, okay? So y equals x squared plus 3 has one y-intercept, but it has no x-intercepts. We're used to things having at least the one x-intercept, but this one has no x-intercepts whatsoever. But if I look at that blue graph, so y equals half x squared minus 1, I do still have my y-intercept, which parabolas always do, but I've actually got two x-intercepts. So what we're seeing here is we can actually have different numbers of x-intercepts being 0, 1, or 2. Now, when you go to graph a parabola, you can still fill in a table of values like usual. And what you'll see when you fill in that table of values is there is a point in your parabola where you can essentially draw like a mirror down. Okay, so if I kind of draw a mirror down here, it splits my parabola in half. And we call that point where it splits in half the turning point or the axis of symmetry. Okay, so every parabola will have a point where it just kind of reflects onto the other side. And you'll be able to see that in a table of values. Now, table of values still work the same as with a linear graph. We just have to be careful with our order of operations, being that your power is going to come before your multiplication. Okay, so I'm going to start by finding out, well, what happens when x equals 0 here? If I do that, I'm going to sub in 0 into here. 0 squared is 0, and if I times that by 2, I'm going to get 0. So just like our linear graphs, we can see that we've got our y-intercept at x equals 0. Okay? If I now sub in, let's say x equals 1, I'm going to have y equals 2 times 1 squared, which is 2, because 1 squared is 1. Multiplying that by 2 will give me 2. If I now do that to 2, following that same pattern, I'm going to have 2 times 2 squared, which would give me 8. Okay? And then for x equals 3, I would end up with 2 times 3 squared, which is 18. Okay, so it doesn't follow a pattern like linear does. You can't just add the same number each time. You do have to do some calculations here. Now, let's have a look if I go over to the left instead. If I do that and sub in x equals negative 1, I'm going to do negative 1 squared, which, remembering, a negative times a negative is positive. Okay, something really important to remember there. So I'm going to have 2 times positive 1 gives me positive 2. And now some of you will be able to fill out the rest of that table noticing what's going on here. But if I sub in negative 2 again, I've got negative 2 squared is positive 4, and times that by 2 gives me 8. So what's happening here is that my reflection point would be at this 0, 0. That's that axis of symmetry I was telling you about before, that turning point. So my parabola is going to look like this, but this part here is going to be 0, 0. Okay? So we still follow the same steps as a linear graph by filling in that table of values, but we do have to find that little turning point there. Now, let's move on to this one here. Some things to note here, which you might have already picked up on, is this negative means that it's reflected. Okay? So instead of being a U shape, it's going to be upside down. It's going to go the other way. Then I've got that plus 3 here, okay, which means that we've moved up 3 from that 0, 0, okay? But you'll be able to see this once you start plotting these points later on. Now, if I, once again, I'm going to start by subbing in 0. I've got my x equals 0. And I'm going to sub that into here, plus 3. I've got 0 squared is 0. Negative 0 is still just going to be 0. So this would be 3, which, remember before I said that number on the end is going to be your y-intercept. Okay, so I've got my y-intercept 3. If I sub in x equals positive 1, this is where I have to be really careful about my order of operations. Okay, because I have to do that squaring before I do the negative. So I have positive 1 squared gives me positive 1. And then making that a negative makes it negative 1, which would give me 2. So at positive 1, I'm actually going to be at y equals 2. Same thing if I was to sub in x equals 2, is that I have to do the power before I do the negative. So this would give me negative 4 plus 3, which gives me negative 1. So see how that's actually going down rather than up from that y-intercept. If I sub in x equals 3, I'm going to have negative of 3 squared plus 3. 3 squared is 9, which means this will be negative 9 plus 3 gives me negative 6. Okay? Now you can have a go subbing in those other points, but if I sub in x equals negative 1, what I'll see is that I end up at the same point that I did with positive 1. Because negative 1 squared is positive 1, I make that a negative, add on 3, and that gives me 2. So for this one here, we're reflecting once again, we're kind of mirroring it at our y-intercept. So this here is once again our turning point or our axis of symmetry. Okay, so because of that squared in our quadratic, our negatives when they're squared become a positive. So we kind of end up with the same answer for our negatives and positives in this form.